In this video, we're going to talk about asymptotes and other discontinuities. If we have a rational function of the form f of x equals p of x over q of x, we can often simplify by crossing out like factors from numerator and denominator. There will be a hole at x equals c if the factor x minus c was originally present in both the numerator and denominator, and if the degree of that factor in the numerator was greater than or equal to the degree of that factor in the denominator. So in other words, if x minus c is present in both numerator and denominator, and if after simplifying it's completely crossed out of the denominator, there's a hole there. And to determine the y-coordinate of the hole, we just plug the x value into the simplified rational expression. Now, there's a vertical asymptote at x equals c if after simplifying the denominator equals 0 at x equals c and the numerator does not equal 0 at x equals c. Now, we can look for holes or vertical asymptotes in one single analysis. And then in a separate single analysis, we can look for horizontal or oblique asymptotes. If we, again, have a rational function of the form f of x equals p of x over q of x, we should simplify by crossing out like factors from numerator and denominator. And if the denominator is degree 0, no more x's, then there won't be any horizontal or oblique asymptotes. Again, that's if the denominator is degree 0 after simplifying. But if the denominator is not degree 0, then again, after simplifying, then there will be a horizontal asymptote at y equals 0 if the degree of the denominator is greater than the degree of the numerator. There will be a horizontal asymptote at y equals lead coefficient of numerator over lead coefficient of denominator if the degree of the numerator equals the degree of the denominator. And again, remember, the denominator must be at least degree 1 after simplifying. There must still be x's there after, at least one x there after simplifying in the denominator. And finally, there will be an oblique asymptote if the degree of the numerator is greater than the degree of the denominator. And again, if the degree of the denominator is at least 1 after simplifying. And to determine the equation of the oblique asymptote, we'll use synthetic division or long division. So for example, suppose we were given the function y equals 2x minus 2 over x squared plus 3x minus 4, and we wanted to determine equations of any asymptotes and locations of any holes. Well, to do this, what we're going to do is simplify the numerator and denominator through factoring. And when we do that, we get these expressions here. Now we can cross out x minus 1 from numerator and denominator, and we ultimately simplify to 2 over x plus 4, but we see that x cannot equal 1. That means we're going to have a hole at x equals 1. But we're going to have a vertical asymptote at x plus 4 equals 0, or in other words, x equals negative 4. So we've got that vertical asymptote at x equals negative 4. We've got that hole at x equals 1, but it would be good to know the y-coordinate of that hole. So what we're going to do is we're going to take that x value of 1 and we're going to plug it into the simplified expression 2 over x plus 4. When we take a 1 and plug it in for x, we get a y value of 2/5. So we end up being able to say there's a vertical asymptote at x equals negative 4 and a hole at 1, 2/5. Now, this next question, we're going to determine equations of any asymptotes and locations of any holes. We've got y equaling 5x plus 15 over 2x plus 12. Well, we simplify and we see we can't cross any factors out. We still have terms with x in the denominator. So we're going to have a vertical asymptote where x plus 6 equals 0. In other words, x is negative 6. And we're going to now determine if we have a horizontal or an oblique asymptote. Well, after simplifying, we have degree 1 over degree 1. So we're going to be able to say there's a horizontal asymptote at lead coefficient over lead coefficient. Well, to do this, we can go back to the original if we want. The lead coefficient of the numerator is 5 and the lead coefficient of the denominator is 2. So we're going to have a horizontal asymptote at y equals 5 over 2. And now that we know both those pieces of information, we can write our therefore statement in red. Now, for the next question, we're going to determine equations of asymptotes and locations of holes of this function given right here. Well, we take a couple of steps to simplify, and we see that the numerator is 3 times x plus 6 times x minus 1, and the denominator is 4 times x minus 6 times x plus 1. And so we see that we've got a vertical asymptote at x equals 6 and another vertical asymptote at x equals 1. We're just setting these factors in the denominator equal to 0. Now, after we simplified, we see that the degree of the numerator and degree of the denominator are equal and at least 1. So what that means is we're going to have a horizontal asymptote at y equals lead coefficient of lead coefficient over lead coefficient. Well, the lead coefficient of the numerator is 3 and the lead coefficient of the denominator is 4. So this is going to be a 3 over 4. So we're going to be able to say we have a vertical asymptote at x equals 6 and another one at x equals 1 and a horizontal asymptote at y equals 3 over 4. Now for this next question, we're going to have y equals 3x squared minus 15x minus 18 over 4x squared minus 20x minus 24. When we simplify these two and we factor, we get 3 times x minus 6 times x plus 1 over 4 times x minus 6 times x plus 1. Well, we can cancel out these x minus 6's and cancel out these x plus 1's. That means, and there's no more in the denominator, so that means we're going to have a hole where x is 6 and a hole where x is negative 1. So after simplifying, after crossing everything out, we see that we're left with y equals 3 over 4. We're going to take an x value of 6 and plug it into this expression. Well, there's nowhere to plug that in, so we just get a y coordinate of 3 over 4. And again, we're going to have an x coordinate of negative 1. We're going to plug it into this simplified expression. But again, there's nowhere to plug it in, so we're going to get a y coordinate of 3 over 4. So we're going to be able to say that we've got a hole at negative 1 3/4 and a hole at 6 comma 3/4. Well, that's the hole / vertical asymptote analysis. You might be wondering, how about the horizontal / oblique asymptote analysis? And the answer is there isn't one to do. Because if you recall, the point that we were trying to make pretty strongly was if after simplifying there are no more x's in the denominator, you don't have any horizontal or oblique asymptotes. So there are none, and so we're just left with a couple of holes. Now, what if we're given this expression here, y equals x squared minus 2x plus 4 over x minus 3? Now, the numerator doesn't factor at all, so there's no simplifying we can do. We're going to have a vertical asymptote at x minus 3 equals 0, which is another way of saying x equals 3. And since we were not able to cancel out the x's from the denominator like we did in the last question, we're going to say that we have to engage in our horizontal or oblique asymptote analysis. So in this case, we know we have a horizontal or oblique asymptote, and we see that we have a higher degree in the numerator than in the denominator. We're degree 2 over degree 1. That means we're going to have an oblique asymptote. And to determine the equation of that oblique asymptote, we're going to use synthetic division. And before we see that on the next slide, we'll just do it quickly up here. We've got this expression here, so we're going to take that x minus 3. We'll represent that by putting a positive 3 to the left. And we've got x squared minus 2x plus 4. So we'll represent that by writing a 1, a negative 2, and a 4. We'll drop down the 1. 3 times 1 is 3. Negative 2 plus 3 is 1. 3 times 1 is 3, and 4 plus 3 is 7. So we're going to be able to say that y is therefore equal to 1x plus 1 plus 7 over x minus 3. Now that's what the function is equal to, but the oblique asymptote will be this portion right here, the y equals x plus 1. So we'll see that on the next page here. And just if the synthetic division is a little bit, you need a little bit of a refresher on that. We've got the 1, we drop it down. We then do 3 times 1, which is 3. Negative 2 plus 3 equals 1. 3 times 1 is another 3. 4 plus 3 is 7. Since this was degree 2 and this was degree 1, our result will be degree 1, so 1x plus 1. But then we'll have that remainder of 7 over whatever that part represented, which is x minus 3. And so that means our oblique asymptote will be at y equals x plus 1. We already established where our vertical asymptote was. And now for this question, we want to determine constants a and b such that the graph of this particular function shown has a horizontal asymptote at y equals 8 and a vertical asymptote at x equals negative 5. Well, if we have a vertical asymptote at x equals negative 5, then that means when x equals negative 5, that denominator, bx minus 1, must be equal to 0. So b times negative 5 minus 1 must be equal to 0. That's like saying negative 5b minus 1 is 0. Or in other words, negative 5b is 1. Or in other words, b is negative 1 over 5. So we know that b must be negative 1 over 5. Now, a horizontal asymptote at y equals 8, since we have a degree 1 over degree 1, that must mean lead coefficient over lead coefficient equals positive 8. So a over b must be equal to positive 8. But we just said b is negative 1/5. So that means a over negative 1/5 must be equal to positive 8. And that's what's written here. And one step later, we solve by multiplying left side and right side both by negative 1/5. We get a is equal to negative 8/5, and then we can write our therefore statement in red at the bottom of the page.